So the main bulk of the exam is on chapters 4 and 5. Chapter 4, continuous random variables. Chapter 5 is bivariate random variables in both the discrete and continuous cases. Just a quick summary reminding you what we've done. So there's just the definition of really a continuous random variable PDF, little f of x, being something that's going to be non-negative for all x and has to integrate to 1. And in general, you want to keep things simple. You want to allow the entire real number line here. And so that just keeps things simple in the abstract, but in practical examples, you can often do a smaller interval. The only one where we couldn't do this was the normal distribution, where we had to use the minus infinity to infinity. The corresponding CDF, capital F of x, is the probability that the random variable is less than or equal to little x, and that means you integrate the PDF from minus infinity to x. Use a different variable like c if you like, or t, or u. And by the fundamental theorem of calculus, this does mean that the derivative of capital F is little f. Capital F is an antiderivative of little f. Not any old antiderivative. Its value at minus infinity has to be 0. I say that with quotes. It has to have a limiting value of 0 as x goes to minus infinity. Though if, as in many applications like gamma distributions, exponential, chi-squared, lifetime random variables, we start the positive probabilities at 0. So that can be a 0 there. And we can also say capital F of 0 is 0. You got your expectations. In general, the book writes the expected value of a function of x is found by integrating that function times the PDF. Technically speaking, you need to assume various things about convergence to guarantee this exists, this improper integral. And there are examples where it doesn't exist, but most of our examples it did. The most common things for h of x are x squared, x minus mu quantity squared. That's the definition of the variance. Yeah, the mean is still expected value of x. The variance is still the expected value of x minus mu squared, which by the computational formula is the second moment minus the first moment squared. All the stuff about moment generating functions from chapter 3 still works in chapter 4. The kth moment can still be found by differentiating the moment generating function k times and plugging in 0. That's what that notation means. That means kth derivative. That's a k there. Standard deviation is still the square root of the variance. We still have properties of expectations, like it's linear, and properties of variances that you learn in chapter 3. They still apply in chapter 4, right? I'm talking about things like this. This still works in chapter 4. In chapter 4, it still works that the variance of a sum is the sum of the variance, but only if x and y are independent. Although we didn't learn until chapter 5 what that really meant. In chapter 3 and 4, when we talked about this formula, we treated independent random variables as intuitive. The values that y takes on is not dependent on x intuitively. It's not until chapter 5 that we saw this means that their joint PDF is the product of their individual PDFs, which you could also call the marginal PDFs. In other words, you're assuming something about the joint PDF when you assume x and y are independent. You're using the individual PDFs to create the joint PDF in that case. We also in chapter 4 had various special distributions, gamma, chi-square. Normal, you want to make sure you get practice computing probabilities with those. I would encourage you to do it both with your calculator and with tables. Get some practice with that. It is, even though we got our high technology, I think it's good to practice with the tables. I mean, if nothing else, in the normal case, we often convert to Z, and Z is standard normal if X is normal with mean, mu, and variance sigma squared. That's just good to know and practice with, just to make it more real, more concrete. Be able to understand those kinds of things in books when you're reading these kinds of examples. There's the normal approximation to binomial. Which involves the half unit correction. There was also the 68, 95, 99.7 rule of thumb. There's also Chebyshev's inequality, which I really haven't emphasized. There was one homework problem about it. I don't think I'll put Chebyshev's inequality on the exam. Then we have the stuff about actuarial science. The two handouts, the first one being on the lifetime random variables, the second one being relating that to the time value of money. So you got a lifetime T that's of a newborn baby or appliance, and you can also consider the corresponding remaining lifetime variable labeled T sub X by actuaries or T of X on the handout to be T minus X. You can use your survival function with various kinds of notations to figure out the CDF, the PDF, and the force of mortality. You can also, I emphasize, if you're given the force of mortality, figure out the survival function. It's like e to the negative integral of the survival function. There's also the Darth Vader rule for computing the mean in the second moment with shortcuts involving the survival function. There was the stuff about the Curtate random variable where you round the value of T down to the nearest greatest integer less than the given value of T. I won't test you on that. In the second handout, hang on here, there's the stuff about interest rate, force of interest, discount factor. Force of interest is ln of 1 plus I. Discount factor V is either negative delta or 1 over 1 plus I. And figuring out present values. There's a present value random variable for a future payment, and we call it the Z bar, and its mean could be found in the usual way with an integral. And there was stuff about annuities, but I won't test you on the annuities. Then we had the chapter 5 stuff, which I won't take the time to talk about. But yes, there is a video where I work through practice problems. I'll share that with you. Okay.